think so. Oh, we're already recording, so. Okay, I think we're good.
Yeah, I don't think that's fair. Are you chairing this? I am chairing. You were checking this one. I'm chairing this session. I just wanted to check off who your technical support person was. This is the trickiest of all the computers, and I wanted to make sure that you, and it's going to extend the desktop, and I just want to make sure that you understood that that's going to be a challenge. Do you have any remote presenters? Yeah.
Yes, we do. Check the sound.
Yeah, no, it's just a matter of making, it's just a matter of making sure that you get the right Zoom thing, and so if you're okay with it, that's fine. Yeah. No, so I've been a couple of them where they're just like. Okay, so that was my good to you today.
Thank you.
Good luck, and I hope you have a fabulous session. Thank you very much. I will be wonderful. I'm sure you will. You're good, Jack.
Yes.
And your co-researcher today.
Yes.
That's everybody. I thought it would be there. I should have done. Okay.
Sounds.
It does sound serious. And there's only like 30 people on the United States. Yeah, meetings coming up near one. I don't think there you go. You have a nice I have a white ball in the hair. No, it wouldn't know. I love different versions. I understand. When I went to Rome, pictures of Germans. The Germans of mine. I can't believe how many.
So evolved new and you know how far and back.
Oh, that's not.
This one has a aerial view. That shows the background view. And actually, it's about it's like the wind. So someone else said, and so. So this is me when I'm backing around in the drive. So, and that is really what that was like. Yeah, so they will be, yeah, right again.
I think it's time to get started. We have 5 speakers at this session. And so I have discovered in a 5-speaker session, it's almost impossible to get questions in between people. So please save any questions for the end, and hopefully we'll have a few minutes after people have spoken. And of course, everyone is encouraged to communicate with the speakers and with each other in the Whova app, etc. So I'd like to welcome you. I'm Lora Lennertz, and I'm from the University of Arkansas, which is in the mid-south of the United States. And our first speaker today is Wolfgang Zenk-Möltgen, who works at GESIS, Leibniz Institute for the Social Sciences in Cologne, Germany. He has studied sociology and political sciences, but he has also worked as a developer for database applications and documentation software. He has worked with the DDI Alliance and is now a member of the DDI Alliance Scientific Board. His presentation is structuring metadata workflows to support data sharing. Please help me in welcoming him to the podium.
Thank you, and I'm happy to present our work here now. First of all, I would like to thank my colleague Uwe Jensen, who prepared this presentation with me, despite he is just shortly before this conference retired. So he cannot be with us, but I'm really grateful for his work. So I'm going to talk about our metadata workflows that we implemented at the GESIS Data Archive. And so where did we start? We are coming from a classical data archive approach, documenting data after the fact. So when we get it, the project was finished and we used the DDI lifecycle standard to document it. After that, we were adding also more features with DDI. Oh, sorry, I said DDI lifecycle, DDI codebook, I'm sorry. Then we added DDI lifecycle features later on to support also projects that we have at GESIS who are active in also collecting data. And when they have repeated waves, they would like to reuse things from former waves. So we managed to do that, but we discovered that there's only a limited number of reuse of elements because we introduced this on the existing tools. So, and now we are also changing, like many archives in the world, we are facing a greater variety of data types. For example, we are having a big project at GESIS about digital behavioral data, and they will also create new data sets that we are currently not being able to archive. And so I choose these pictures of the tornado here. It's from a former DDI publication to show that the metadata that is around the social science data that is always flowing around in this circle, and the archive is somehow in the middle of this tornado. So we also have a kind of split up our tools between the study level and the variable level documentation. We have our data catalog. It's searchable on the homepage. We also provide it via OEA PMH to others. Among those for the CESTA data catalog, where you can, where these records are being harvested. But we also have the variable level documentation made available with a Nesta server, our SARCAD service. But this has now ended because the Nesta software is out of service. And so currently, the variable level documentation is not searchable, and you can only find it in our PDF variable reports that we publish. So we were looking for an approach where we could integrate those sources of metadata to make it searchable in a common way, and also provide the variable level metadata again on the web. So for that, we created a pipeline with different steps. With the beginning, all the legacy system that we use. I will show you later on some of those. So we already had the structured metadata that came out of our legacy systems, but they were different in their DDI compatibility. And so we tried to make all those experts work into DDI lifecycle, and then to put all this metadata into a centralized repository. So this repository is a DDI FlatDB repository. It was presented at former IASSIST already, and this is now our current what we call single source of truth. After that, there's a search index software, Elasticsearch, doing an index so that it can be searched quickly, and this is then used by our website. So to give you an impression what the workflow looks like, so the study level is here. We have the DBK, which is a German abbreviation for our data catalog, and the metadata from that was used for a news feed, and also for the DARA system where we register DOIs with DataCite. But it was also exported to several variants of DDI. So we have DDI Codebook and DDI Lifecycle, and we have different variants of those standards for different purposes. So this was a quite complicated thing we are facing, and the variable level documentation comes from a program called DSDM, and we produce DDI Lifecycle from this program, which is actually based on Microsoft Access databases. Also, then we have another tool called Codebook Explorer to produce our variable reports in PDF. And it also creates some DDI that we need to integrate into our DDI FlatDB. And on top of that, there's the Elasticsearch index, and this is used by the GESIS search. So the Explore Data metadata pipeline is highlighted here. So we did not care so much about the study level, but we integrated the study level into our pipeline. So the report is now what were the challenges that we faced with that project. So we, for example, we did XML transformation scripts to integrate the study level with the variable level XML, but we also used it to integrate the different languages, because in the legacy system, there's a single study for each language, and we needed to integrate that again. So to have those XMLs that we need to integrate, we needed to do database exports. And to get it into the DDI FlatDB, we needed to do database imports. So we are using really a different variety of technology, and that was a challenge in the project. Also, the issue of updating, adding and deleting studies was more difficult than we saw before, because also within a study there might be minor updates. You want to integrate this into your pipeline, and if you have triggers that that make those updates available to a certain step in this pipeline, then you have to make sure that you miss no step, because otherwise you will lose data, and that was also a challenging thing. And last not least, checking all the things that we put into a pipeline, because it's transformed in several steps. We needed to make sure that in the end, all the correct metadata is there. And that was even more complicated. And I will talk a bit about this, how we approached that. So in the beginning, we had a team of people doing manual testing. So I will show you just one example so you see how the system looks like. You can, on our website, you can first select the GESIS data archive as a source, because the website also does a search on publications and other types of objects. So you have then the metadata from the data archive. And if you then have a facet called research data, you find all the data set. So I'm using the example data set from the General Social Survey in Germany called ALBUS. And to find specific variables in there, you can use a facet. You can also filter by study, but you can also enter search keywords. And I'm going to use the meditation keyword to find variables that contain information about meditation. And that's how it looks like. I hope you can see it a bit. I tried to increase the size. So here we are with the facet research data. On the left hand, you see this blue box indicating that with my current search, I have found 103 research data sets. And I have already selected the filter ALBUS for the General Social Survey. So it's 103 studies from ALBUS. And you already see that there are more than 13,000 variables, which is a different facet. But since you are in the facet research data, you see the list of studies down there, also presented with a short view. And people who know at that stage already that they want to download or want to see additional PDF documents on the right-hand side, they can directly access this. If you switch to the variables facet, I have also now here this screenshot already with the search keyword meditation. So then you get a result list of variables instead of data sets. And you see that here, in this case, you have found a variable with the label meditation in it, and it's about Zen meditation. But if you go further down, then you also get other variables. And if you're not limiting yourself to a specific study group, you have the option with the filters on top to select a study group like ALBUS. But you see here also that we have variables in the European Value Study or in some of the Eurobarometer series. This is how the result list looks like for the variables. And we also find variables about yoga and about inner reflection. So that's already quite informing for people if that's some data that they want to use in their study. So maybe you see on the right-hand side, there's also a bookmark action. So by repeating these searches, you can then select specific variables that you like, bookmark them, and see them on one screen later on. And for the detailed variable U, we also display the question text, interview instruction, and also answer categories. Here you see that this is a grid question, so you also have item categories before that. So we have found the fourth item here, but it's really nice that you can see also which other items belong to that grid. And also you see below that the variable code list. So if you scroll further down, you see the codes. And for certain studies, we also have frequency tables and crosstab tables available. And they're supposed to be the same, which we use for the variable reports in our PDF. So that is the same information, but it's searchable. So for this human testing, this was only a small example, but we were approaching all the people responsible for certain survey series and said, look on it. And it resulted in a huge amount of work because they are checking all the variables. And so then the question came up, are the result numbers of the search right? Are the texts right? Are they complete? Can I really find what I need to see in the user interface? And so there are a lot of questions, and we tried to separate this a bit and make it easier by checking the numbers with some automated testing. So that only some small items are really compared between the printed codebook and the web output. And for the automated testing, we approached this by asking ourselves, what are the criteria that we can really check? And so we came up with the completeness thing. So we're counting studies, we're counting variables. So in the beginning, in our tool, we know exactly which study is to be published. And if we collect the numbers that are the expected ones, we can compare it at every stage of the workflow, and ideally with the last stage that it matches. And so the number of studies as a total, but also the number of variables per study and the number of languages per study are criteria that we wanted to check. And we started with a small Excel table, and in the background we created a macro that inserted all the expected values for each study, and then did a web service call to one of the components that I showed before, counted it, and we did a comparison. So that was already a good help. But then we took it one step further and defined these parameters really in a metadata schema that we rendered in XML. So now you see an example of this schema here. We call it metadata expectations. And it's containing, first of all, the repository expectation, where we have the number of studies for the whole repository and the number of variables for all of them, and so on. And then for each study that is in the repository, we have a study expectation. And so you know exactly if you update this file all the time, a new export is being triggered, then you know what is expected. And then we can run a routine check that is automated every day or every hour or whatever we need it for. What is currently work in progress is also to show this on a nice dashboard so that you don't need to go into any XML to see the results, but this is not finished yet. We're using Allure for providing this dashboard so that you can see immediately if all the tests have been completed. And if for those tests which have not been completed, you also see a small message indicating, okay, the expected number of variables was this, but the actual number was lower. So you can go into detail and search what the error was. So the collections that are currently covered are from our DSDM portal. That these are the full codebook documented studies, the big survey series that we have in the archive. You see them listed here, like ISSP, Eurobarometer, the General Social Survey, European Values Study, and so on. But we also realized that we have a lot of studies where we don't have this full codebook or variable report information, but we still have the metadata that is contained in the SPSS files. For most studies, we have those SPSS files because it is still the main archiving format. Even if we have data files coming in, we're converting them routinely to SPSS because people are requesting that sometimes from us. And so we have those available, and we created a small Python script that reads the SPSS metadata and directly creates the DDI lifecycle output from it. So, and you see listed some of these studies that we currently have in our search that is online on our website. For example, the Eurobarometer, it takes also some time before the real big report is ready. So then before that, the SPSS file is ready, so we can, the pre-releases are being included in that. So these are the actual numbers. We have now 1,500 and something studies covered. The total of the archive is 6,400. And I know that at least for 2,000 to 3,000 studies, we have the SPSS files available. So we're planning to add that in the future. So one word to the languages. We're currently restricting the language search on our website to English and German because this is the most common case. We have a lot of languages available for the European values study, and we're going to add that as well, but it's technically more complicated. And so currently we're not having that on the web. So I'm quickly trying to cover some lessons learned. I don't know, my time is nearly over. I think the most important lessons learned is that we really need to plan for such a project beforehand, what will be tested in the end, so that the expectation is right. It isn't only true for simple numbers that you check, but it's also true for the overall thing. What do you want to achieve? And beforehand planning for what will you be testing automatically and what will you give to your users or your data providers, because they are the experts for their data. That is really important. So you can do a broad range of tests always, especially if the user interface is also being developed. And that is something that you need to account in before as well. So, and then my last slide on that is that we also need to make clear that the internal organization, how errors are being worked on and being corrected, that you need to plan that beforehand. We have been using GitLab. So, and some developments for the futures were already mentioned. We will add SPSS metadata for more than 2,000 studies, and we will expand the languages, and we will prepare with our digital behavioral data and to be in the eye of the tornado. Thank you very much.
Let's see if this works. It does. Our next presenter is not being presented here, but he will be presenting virtually, which is something that's different from what your program indicates. The person who will be speaking is Sainyam.
Excellent.
Excellent. Sainyam Galhotra. And Sainyam will be presenting the work of himself and his colleagues, Gong and Raul Castro Fernandez, all from the University of Chicago in the United States. And the title of the presentation is Goal-Oriented Data Discovery for Effective Analytics. Thank you.
Hi, everyone. Can you hear me well?
Yes, thank you.
Okay, yeah, sure. I'll get started. Hi, everyone. I'm Sainyam Galhotra. I'm a postdoctoral researcher at the University of Chicago. And today I'm going to talk about how we can develop effective search tools to help scientists find data sets. To make this problem a little more concrete, let us look at an example of a stock trading firm. This is Bob, who works at the trading firm, and today's task for Bob is to find top agricultural companies in which his company should invest in. So what Bob does is he creates a list of different companies in this agricultural domain, and he wants to rank these companies based on the likelihood that this company would be the most profitable in the next future so that they can invest in those companies. So to solve this problem, Bob is looking for a data set which looks something like this, where we have the different company names, different attributes for those companies, which are like revenue, number of employees, stock price, and so on. Once we have this data set, Bob can perform an analysis on this data set to rank the companies. Now the question is, how can Bob construct this kind of a data set? Let's look at some of the options. First, Bob could use an in-house data set based on the information that the stock trading firm already has about these companies. Or Bob could ask his friends to give some information about these companies, or he could search in the database in the repository they have. All these ways are fine, but they're not the best because they may not be very up to date, and it's very context dependent based on what his friends know and so on. Instead, one of the most promising ways for Bob is to search over data repositories over the web to get more information about these companies. And for this talk, we'll focus on this aspect of search, where Bob is looking into data repositories and wants to find the best data sets for these companies. And we are going to focus on only the tabular data. With that, I would also like to mention that finding data sets is a very difficult task because there are heterogeneous number of sources on the web. There are millions of data sources which contain information in different formats, different amounts of noise, and the scale is a big problem. Given so many challenges, we asked the question, how can we build effective search tools to help Bob find useful data sets? Let's go back to the example and see how Bob could have done this using the current set of tools. So what Bob does is Bob goes on to Google dataset search. He types the names of the companies in the search engine, gets a list of datasets, which are shown here on the screen. Amongst these datasets, as you can see, there are datasets from different sources. So Bob is confused. How should I combine these different data sets? There is lack of metadata information for many of these data sets. So it's unclear which of these data sets should he use for the analysis. Next, when he searches for a company like CHS, he's even more surprised because there are many data sets which don't refer to the company CHS which he's looking for. For example, there is a data set on community health survey and so on. So now Bob has even more challenging task to remove noise from the data sets and find the best data sets for his task. So he needs to figure out how to search, how to shortlist, how to remove noise, how to combine these, and then worry about the analysis also. So what Bob does is Bob says, I'll list top 100 data sets and go over those manually. So in this manual approach, Bob looks at the title information, the source information, the metadata, whatever is available to decide whether to keep a data set or not. And with that, Bob comes up with a pipeline. What Bob does is Bob identifies various data sets, which are about market share, revenue, customer satisfaction, whatever he could find using his search knowledge and his domain knowledge. He shortlists those data sets, then implements the code to prepare those data sets, which is cleaning the data set, remove noisy characters, homogenize them, combine them, create a single table, and then perform prediction like machine learning tasks or analysis to rank the data set, rank the companies. Now, this is all good. After spending so much time, Bob has a ranking of the companies, but Bob is confused. Did I get all the data sets that are out there? Are there more data sets that Bob could have used to improve the classification or the analysis? Because there's a direct financial impact to his decisions. His decisions are very high stakes. So he wants to make sure that he got all the information that is available on the web in the data repositories. And that is not the case out here because Bob had to use his own knowledge, and whatever he knows is what he could search for. He could not search for anything that he doesn't know about. Now, to help Bob resolve this doubt, let's see what else we could do. The question we ask is, can we use metadata information to help solve the problem? So suppose in a hypothetical scenario, we enforce that anyone who publishes their data sets on the repository populates metadata. By metadata, I mean the title information, author information, dataset source, or even the description. All this is good, but even if we have all that information, Bob does not know what should he search for. Should he search for company revenue, customer satisfaction, what attributes? Rather, if each data set had a metadata which corresponds to the correlation of that particular data with the company's stock prices, that's an ideal metadata for the Bob's task. But getting such metadata is not very realistic because this kind of metadata is very task dependent. It varies from different, like if another Bob comes up with a different task, we need to have a different kind of a metadata to help Bob. So there's a lot of repetitive process of processing these data sets for each different task, and we want to avoid all those repetitions. So in summary, what we want is that we don't want the users to repeat the search, And we want to reduce the reliance of the search results on the human knowledge, because human knowledge is very varied and each user has a different human knowledge. And what we want is, we want to reduce Bob's effort, and we are okay that Bob can monitor the search results, monitor the search algorithms progress, but we want Bob to give as minimum information as possible. We want the search algorithm to search over the whole repository and not just a small subset of it. And we want it to handle the large scale amount of data present online. And to solve all these challenges, what we propose is, let's ask Bob to implement the software, which is the machine learning analysis algorithm, and give it to us. So Bob and Bob is an expert in that because he's supposed to do that analysis. So Bob implements that algorithm, gives it to our search algorithm. Our search algorithm works with the software that Bob has written to find the data sets which are best for that analysis algorithm. That is the high level intuition of our approach. So in some sense, we have automated the whole pipeline, where the pipeline is going to search for the best data sets for Bob and will require the least amount of information from Bob. To look at it in more detail, let's look at an example. So this is an open data set from the US government websites, which contains information about different counties. And we want to do a poverty analysis about different attributes that will help us analyze the poverty situation in different counties. When we used our approach, we identified many different data sets. And as you may see, there's some of them which are slightly unintuitive, but they're quite interesting to see. For example, we identified the number of taxi pickups is highly correlated with the poverty information in different counties, or the number of businesses in each region is correlated with the poverty in different counties. And these are some of the data sets that we could not come up with our own domain knowledge, but when our approach suggested, it was like, oh yeah, this makes kind of some sense. Let's look at another example of a classification task where we have information about the schools in New York City, and we want to analyze how the students are performing in each school. So this is a classification task, and let me briefly show you the demo for this task. So we built a simple user interface on our approach where you can upload the data set. So let me upload this data set. When we upload the data set, our approach identifies the different data sets that it finds. So in summary, it found around 12,000 data sets for this school's data set. And I don't know if you're able to see, but the different data sets contain like engagement score of students, the school type, principal names, academic expectation score, and so on. Then you can mention what task you want to perform and what you want to predict. So I choose the attribute class, and the optimization objective is F-score. And when we run our approach, it identifies that there are a total of 4 data sets amongst the 12,000 which were identified. And only these 4 data sets are actually useful to optimize the F-score of the classifier. So when we show, so in summary, now Bob has to just look at these 4 data sets to figure out which ones he wants to keep, which ones he does not want to keep, because all other data sets are not helping with that task. So in summary, our approach has removed all data sets that are not very useful for the task. Going back to the presentation, I'll briefly summarize what our approach does. Our approach is a general approach that helps to optimize the utility of the downstream task which Bob wants to perform. It's very general, which works with different applications like causal inference, classification, regression, clustering, and even natural language processing related tasks. I won't go into too much detail of our approach, but at a high level, what it does is we have an input collection of data sets, which I show with the different files here. What our approach does is it looks at the different properties of these data sets, clusters these data sets into different groups. For example, we have the white cluster on top left, yellow on top, bottom left, and the blue one. Once it clusters these different data sets available in the repository, it ranks the representatives from each cluster. So suppose this is the ranking, then it chooses the first element in this ranking and queries the Bob's software with that data set. And the Bob's software says that this data set is maybe performing 0.7 on, is giving an F-score of 0.7. Using that information, our approach re-ranks the different representatives, chooses the next representative in the ranking, queries the Bob's software again, and figures out which ones are the best. And using this iterative process, in the end, it identifies that these are the small subset of data sets which are going to help Bob's application. So in summary, our approach does not require much human input. It in fact requires the software implementation for the downstream analysis that the user wants to do. It is efficient to handle large scale data, and it is guaranteed to optimize the software that Bob has written. Before I end, I would also like to mention that I'm not from the IASSIST community, and this is the first time I'm attending. So I would be happy to talk more about your applications and the things we could work together on to build data search and discovery tools. Thank you.
Thank you. And I'm very happy that Bob was interested in an Arkansas company, Tyson Foods. I'd like to introduce our next speaker, please. If you can, he's sitting over here. Our next speaker is Merlijn De Smit from Stockholm University. A little bit about his background. Oops, or maybe not. There we go. His background is as a researcher in Finno-Ugric linguistics, and have been working as a data steward at Stockholm University Library since September 2021. He's working with researchers in humanities and social science fields and is currently mostly engaged in network building, educational and outreach efforts. His main interests are in historical linguistics, research methodology and philosophy of science questions, programming, and computer games. Let's please welcome Merlijn De Smit.
Here? Okay. Okay, thanks very much. I'm going to present the RDM infrastructure at Stockholm University.
Oops, I see.
Okay, I'm going to present the research data infrastructure, research data management infrastructure at Stockholm University and some of the challenges we are facing. So, wait a minute. So, some basic history. The RDM infrastructure started out as a research data project in 2016, where a work group developed concrete plans for setting up an RDM team. And also during that time, collaboration with the Swedish National Data Service was established, as well as our support email address, opendata@su.se was introduced. And during the following year, 2017-2018, these plans were implemented. The RDM team was initiated, and also the guiding policies at the university level were developed. And in more recent years, 2020 to 2021, 2022, we introduced some of our technical tools, which I will talk about a little more in a little while. The guiding policies we're dealing with is, first of all, the overarching Swedish government policy, which demands a transition to open science practices by 2026 at the latest. So this is basically what we have to kind of follow. Locally, there has been a university research data policy since 2018, which announces support for FAIR principles and mandates setting up an RDM infrastructure. And in addition to this, we have the more concrete rules for research data management, which, for example, state that research data should be as public as possible, managed according to FAIR principles, but also that there should be a data management plan, and that there should be a contact person for research data at each department. And this is something that's not implemented yet, but we are working on it. We have a new open science policy, which is currently being approved, but which will become approved soon. The RDM team is involved in various external projects on the local, national, and international level. Stockholm University is a member of the Swedish National Data Service Consortium. And it is also the host of the Association of the Swedish Higher Education Institutions. And as such, it is represented in the European Open Science Cloud. Various of our team members are active in external projects. For example, Joachim Philipsson's work on machine actionable data management plans has been part of an EOSC Nordic deliverable. And we are also working closely with some projects at Stockholm University, primarily the Bolin Center database for climate research data, but also the Swedish Level of Living Survey, a very big longitudinal study at the Swedish Institute for Social Research. And the current status of our team, we are 9 persons employed at Stockholm University Library, and this includes 2 data stewards, of which I am one, 2 archivists, and a communication officer, and a number of other people. And 6 of us are engaged with research data management questions full-time. In addition, we have a broader team, which also includes a specialist in research ethics and a data security officer. And our mission is basically to assist researchers with management of research data and metadata during the whole project lifecycle, from planning to archiving in the end. And all this in accordance with open science and FAIR principles. Now, we provide a number of technical tools to researchers. First of all, we manage an instance of DMP Online, where we have our own template for writing a data management plan, which I'm going to talk about in a while. Then we provide storage space to research and PhD students, 200 GB free of charge at Sunet's cloud service. We have also recently introduced support for electronic lab notebook, and we manage our own space in a number of data repositories, Figshare, Zenodo, and Dataverse, and also everything that is sent to Swedish National Data Service from Stockholm University is curated by us. In addition to this, the Bolin Center for Climate Research manages its own repository, but we are involved with that as well. Now, DMP Online to start with. We have our own instance of DMP Online, which allows access to a number of data management plan templates from various funding organizations. For example, the Swedish Research Council, but also the Dutch NWO. In addition, we have developed our own template, the SUVR template. And the good thing about this template is that it's mostly multiple choice options. There are very few free text fields, and this makes it easier for researchers who already have to write enough free text as it is. The multiple choice options often contain good hints and pointers to FAIR data practices, and the whole format allows for mostly automatic archiving. In terms of usage, there have been about 56 plans with our own SUVR template since 2020. Researchers at Stockholm University, of course, they use a number of other plans as well, particularly that of the Swedish Research Council, and particularly earlier, the DCC template. Then the Sunet Drive Nextcloud storage solution. Sunet is a data infrastructure, computer infrastructure managed by the Swedish Research Council that connects Swedish universities and a big number of other institutions and public offices. And we provide researchers and doctoral students with 200 GB of storage space at no cost. And this storage space is GDPR proof. The servers are located in Sweden, so it's safe to store personal data and even sensitive data there. In addition to the 200 GB free of charge, additional space is available at €6 per gigabyte per month, which amounts to about 720 kroners per year for a whole terabyte. So that's not very much. It will become much if you have massive amount of data, of course. And the service basically works like any other cloud service. You can share files with others, also people outside of Stockholm University and outside of Sweden. You can sync your files on the cloud with the local folder on your computer and so on. And in terms of usage, we have approximately 450 researchers that use it as of June 2022. And I estimate that this might represent maybe 10% of researchers at Stockholm University. Then our repositories, we curate data sets in Figshare, S&D, Zenodo, and Dataverse. And in Figshare, Zenodo, and Dataverse, we have our own communities. In terms of usage, most researchers appear to use Figshare. There are more than 1,000 entries there, of which 466 data sets. However, the other repositories are used much less, 48 data sets in Swedish National Data Service, and much less in Zenodo and Harvard Dataverse. And in addition to this hard infrastructure, the technical solutions, we have the soft infrastructure of network, training, communication. We have regular webinars about DMP Online, other data management aspects. We organize short courses in research software, for example, Bash and R, together with Karolinska Institute and the Royal Technical University of Stockholm, the so-called Stockholm Trio. And in the spring of 2021, we held an open science course for doctoral students, which we hope to be able to hold again. Additionally, we started visits to departments to inform about the services and about good data management practices. And at this point, most departments in humanities and social science have been visited. We aim to have visited all the departments at some point by the end of 2022. And connected to this, we are trying to build a network of contact persons at those departments to facilitate the information flow, feedback, and so on. And we hold webinars and physical seminars at specific departments on request about, for example, data management plans, storage solutions, GDPR and ethical aspects, and so forth. Finally, we have our RDM support email at opendata@su.se. Now, challenges we encounter. We are the technical tools. DMP Online works pretty well. SoonerDrive Nextcloud, our storage solution, however, it's a new storage solution, which means there are bugs, there are glitches, and some parts are still under development. And there is no automatic backup function, and this scares away some researchers from using it. There are also issues of ease of use compared to other more established cloud services such as Box. And the problem is that Box is not GDPR secure, or is GDPR secure. So we want researchers to use our storage solution, but there are issues with ease of use. And we're at a point that many research departments, particularly data-heavy departments, have developed their own homegrown solutions, and transition to SoonerDrive is not always very easy. As far as our repositories are concerned, this works well, but we want to see them used more. We particularly want to see more data sets. A lot of the documents deposited at Figshare are preprints and slides from presentations and so on, which is perfectly okay because Figshare is also intended for that. But we are the research data management team, we want more data. Also, we see many entries in Figshare, but very few in other managed repositories. And we have no clear picture of the extent to which our researchers publish outside of our own managed space or in other repositories, but we know they do to a considerable extent. In terms of network and communication challenges we encounter, first of all, we need to find reliable ways of communicating with researchers outside of the flood of newsletters, mass emails, because researchers are drowning into newsletters from just about everything. They don't read them, and we can't reach out to them that way. What we have found is that direct contact on specific issues works well. For example, this year we have invited researchers that had received grants to a specific webinar on data management planning, and researchers actually turned up there. So direct contact works. The other challenge is that we need to combine the top-down policies, the transition to open science, with bottom-up assistance on very concrete issues. We don't want to be seen as imposing policies in a top-down fashion. We need to combine this with assistance on storage, data management plans, and so on. So the whole transition to open science practices flows more naturally from the bottom, so to speak. Additionally, there is the issue that a lot of data management policies and so on seem to be adapted to researchers that have a specific project which they can spend most of their working time on. However, many researchers do not have that. They may have 20 or 30% or so of their work hours set aside for research, aside from teaching, administrative activities, and so on. And we need to accommodate these research better. Finally, there are these overlapping areas: data management, GDPR compliance, research ethics, and archiving. And what we want to avoid is a situation where we come to researchers to say, you have to publish your data. Then the lawyers come and say, no, you can't publish your data because of GDPR. And then the ethics people come with their advice and so on. And this is experienced as a burden and very conflicting advice. We need to integrate these areas so that we speak with one voice. Now, in connection with visiting individual departments, I have carried out small opinion surveys. And some of the issues that jump out is that researchers experience that the combination of open science policies, GDPR compliance, and ethical obligations basically constitute a task that they feel lies outside of their expertise, that they are not really competent to undertake. Also, it creates a workload that is experienced as too heavy, that takes the fun out of research, or even renders the research project basically impossible to undertake. Researchers also experience that there is conflict between open science and GDPR. Research may want to publish interview data, but cannot because it contains personal data. The identifying qualitative data particularly is not always possible. It's very often impossible without rendering the data pointless. Finally, we see that there may be conflicts between open science practices as well as legal obligations in Sweden and promises made to research persons. Researchers may promise their research persons that they will destroy the data immediately after publishing. And this they are not allowed to do, and we have to tell them that they can't do this. Now, some solutions here. We need to place more emphasis, I believe, on publishing the metadata if the data concerns personal information. Open science does not imply that everything should be put out on the internet. But if the data contains personal information, just publishing the metadata is very useful. Also, in Sweden, research data is a public document. It's public information that should be archived. But researchers are not always aware of this. I was not aware of it at all as a researcher. So we need to reach out on this issue, which could create an incentive because the demand for archiving at the end may constitute a very good reason to properly manage your research data. However, this requires also that there's good archive infrastructure at a local, the departmental level. As I mentioned, we want to integrate the aspects of research data management, GDPR, and ethics. To speak with one voice, to have common seminars, common presentations, and we pretty much started out doing so. Finally, we need to emphasize concrete local solutions that ease researcher workload. Good standard solutions. I think the SUVR template for data management plans is such a solution. Because if we want researchers to abandon old and well-known practices, we need to give them a good incentive, a good reason to do so. And in conclusion, what I will mention is that if implemented well, open science and FAIR principles, good data management, they make life easier for researchers. They allow better availability and reusability of research data, better possibilities to verify research results. Good planning helps to avoid loss of data, or for example, breach of GDPR legislation. And good data management means that you don't have to worry about resuscitating a broken USB stick. You can concentrate on your research with peace of mind. And a primary task of the RDM team, I would say, is to make sure that the implementation of all this is not overly burdensome or experienced as overly burdensome. Okay, that was pretty much what I intended to say.
Thank you very much. Our next presenter is Dekker, and he'll be presenting materials that he and Yana Hrytsenko at the University of Rhode Island have been working on. Dekker has been a data professional for over 30 years in a variety of roles. In the early 2000s, he joined IASSIST after taking a position at the University of California, Berkeley Libraries. While at Berkeley, he developed the library's first social science data services program and helped launch the university's research data consulting service. After 14 years, he left Berkeley for a faculty position at the University of Rhode Island, where he has helped lead the development of the university's data science education program and library's artificial intelligence lab. At the end of June, he will be stepping down from that position and transitioning to a part-time position as a co-PI on a multi-year interdisciplinary environmental health sciences research project, which will be the topic of the talk today.
Okay, so as that introduction tells you, I didn't really expect to be here. If you'd asked me 2.5 years ago what I'd be doing, I would have told you I would have been climbing rocks in southern Spain or something like that. But sometimes things come along that sound interesting to get involved with. And so I'm currently working on a research project. And I'll give you a little bit of background on the project and some of the FAIR data work that we hope to accomplish, if I can control the screen. Okay, the name of the project is Project STEEP. And STEEP stands for Sources, Transport, Exposure, and Effects of PFAS. This is funded by the NIEHS, which is a federally funded organization under the National Institute of Health in the US, and their Superfund research program, which basically allocates money for and administers university grants on basic biological, environmental, and engineering process to find real and practical solutions to exposures to hazardous substances. Now, mind you, my background's in the social sciences. I don't know a lot about these sort of scientific things, but I have worked with lots of weird data and data formats and done a lot of programming. And as luck would have it, I was sort of the only one they could find on campus who could help them write this grant proposal when the funder sort of introduced some new elements to the proposal. Actually, I initially got involved when a supplement became available to the first iteration of STEEP, which just ended this year. But they found me, we got awarded a supplement to look at some data interoperability issues. And then they asked if I could help write the Renewal Grant, which we were awarded and which begins this year. This is a multi-institution grant. We've got researchers at Rhode Island and also at the Harvard's School of Public Health, one of the PIs also has a co-appointment at the University of Copenhagen. So there's some European elements, and then a nonprofit institute called the Silent Spring Institute in Massachusetts is also involved. A little bit more about PFAS. I won't get into a lot of details, but if you don't know about PFAS, you should. These are evil substances that have been produced for over 60 years, but only for the last 20 years have we known their risk to human health, and that it became something that deserved to be regulated and remediated. So high exposure can lead to a variety of adverse human health effects, including altered metabolic functions, liver toxicity, obesity. And recent studies, unfortunately, have estimated that greater than 47,000 tons of PFAS compounds have been released from consumer products into the environment over the past 60 years. And a large fraction of these releases remain concentrated on or around contaminated sites. There's actually a Hollywood movie called Dark Waters. I'd recommend seeing, that came out in 2019 if you want sort of one story about these compounds. So if you've seen that movie, you've learned something about PFAS chemicals. Just in case you need to be convinced, here's a bunch of bad things that happen to people. Sort of needless to say, there's industry tries to prevent scientists from saying that there is a causal relationship between these compounds and these human health conditions, but there are certainly correlations, and projects like ours are looking at some of the causal relationships between the compounds, what they're doing at the cellular level to do harm to people. So just a little bit of background about how things are organized and how the data part fits in. As I mentioned, the funder required some new, in addition to the regular data management planning, they actually were seeing this the emergence of FAIR principles and other need to do better things to make data reusable. And so they required that anyone trying to renew their grant or going for new grants through this program had to introduce a data management core. So we're one of the primary cores of the grant. There are a variety of other cores. Data management works with all cores. And in particular, obviously, we work with the research projects. We have 4 research projects. I won't go into all the types of data they collect. I mean, it really spans a range of scientific disciplines, from chemical engineering, epidemiology, biomedical sciences. But there is a lot of sort of commonality in the data, because much of the data is collected through techniques that use mass spectrometry instruments. So we're looking for these compounds in either water samples, soil samples, tissue samples from either living things that were once living, like birds and fish that are found in the environment, or through, we do have one team that does do lab work on mice. And so there's a certain type of instrument that's used to gather or to collect these data and to do the measurements. Unfortunately, these mass spec machines tend to use proprietary standards for data, and so that introduces some challenges to making data shareable. There are open standards, but they're not widely adopted yet, so we run into some technical issues there. And then there are a variety of other types of data that get collected. So I lead the DMAC, or the Data Management and Analysis Core, and we have some specific aims that we're trying to address. The team is, as with most funded research, we don't have enough people to do what the funder wants us to do, but we're trying to do the best we can. There's myself, 2 statisticians, a postdoc with expertise in mass spec. Now, all these people are part-time. None of us are full-time on the project. We also hope to have a couple of graduate research assistants, and maybe beyond year 1, we're hoping to bring in a full-time postdoc fellow to kind of lead the more kind of advanced work that we want to accomplish with this research. So with all that in mind, I'll talk about this FAIR reproducibility concept that kind of popped into my head as we started working on the grant, and that we did some early work on during our work on the supplement that we were awarded just before COVID. COVID kind of slowed things down, made it hard for people to get into their labs, made it hard to communicate, what went on. So we ran into some obstacles, but fortunately we got enough done so that the funder had enough faith in us to give us more money to carry on our work for another 5 years. So I don't want to give you the full FAIR principles, song and dance. There's a lot of information about it, but there are some really important concepts that are often overlooked when trying to adopt the FAIR principles. So here I've outlined a few of the specific challenges we're going to address. With our limited resources, we want to develop practices and tools that we can train our researchers to adopt. We want to develop and implement training and documentation approaches, and we need to choose which standards for machine actionable metadata and data to adopt and how to implement them. And that italicized word is the critical one, and that's what I want to sort of emphasize in the sort of brief discussion of the reproducibility challenges of FAIR. So as I see it, and I haven't seen this addressed a lot in the literature yet, but the thing to keep in mind about FAIR is it's not just sort of a nice way to say open data or whatever, but there's this overarching goal of FAIR, which is to facilitate the use of machine learning to generate insights from vast amounts of data. So don't confuse FAIR with open, they're two different principles. So FAIR means preparing data and its accompanying metadata in a way that machine learning algorithms can process it, understand it, make inferences from it. So this can involve the use of controlled vocabularies and ontologies to describe how the data was created. And remember, this has to be machine actionable. So that means that whatever you produce, it's got to be in some sort of structured format. So that means you got to do computation. Computation is going to be involved in altering the data, in creating the metadata, and you're going to be producing the machine readable formats. And all of those basically raise the bar and raise the possibility that you can corrupt the data or produce incorrect metadata. So I've tried to apply the lessons I've learned from open science and the reproducible science movement to this challenge of producing machine actionable data, metadata, and in an attempt to kind of build a framework. We're not going to build a tool that solves things for everyone. We want to build tools that will solve the specific needs of our research project. And I'm going to try to apply these principles that we've learned from open science, use these modular languages like Python and R, literate programming techniques using Jupyter Notebook, so that you can produce things so that you don't get locked into proprietary strategies, and so that you can produce things that you can share with the community, get feedback on, and that any coder can start to apply, so that you can start to use these things with limited knowledge of programming. And when you use them, you can sort of redo and reuse what you've done, or you can reproduce the work that you've done in the past to verify things. Just a very quick outline. I can't really go into this too much, but one really simple challenge that sort of illustrates the need for a machine, the need to do computation on data. A very typical way that our scientists produce data is using spreadsheets. Here they're measuring compounds. Those columns might go out for 50 columns. That is not a data format that can be shared. We want to reshape it into a long form so that we list the compounds out in one column, so that we can create metadata that maps those compound names to some sort of controlled vocabulary. So you have to do a little bit of programming to sort of reshape that data and then save it in whatever ultimate format. These are all steps where you could do something wrong if you were doing this in sort of an ad hoc way. And so we will be producing, for each data set, we will be producing accompanying Jupyter notebooks that have all the steps involved in altering the data. Now, code-based metadata production is going to be, that's going to be the big challenge. It's still very much at a conceptual level, but most of the tools are out there. We're hoping to do, keep the amount of new coding we have to do to a minimum. One advantage we have, though, is that our metadata needs are going to be somewhat constrained given the specificity of the STEEP research. We know what compounds are involved. We know what sort of living organisms and non-living organisms we deal with. So I think we can kind of sort of build a repository of metadata items that we can keep reapplying to the data that we produce, and do that in sort of systematic code-based way, using existing tools or and minimal amounts of new programming. So we have just a brief strategy for the first year, and the last item being very important, which is finding more funding. So I'm going to stop there, and afterwards we'll have question and answers if anyone wants to learn more about what we are up to.
Thank you very much. We may have a very abbreviated question and answer session if people want to maybe stay a little late. We are running a little late. I think this hybrid thing takes a while. So our last presentation is indeed virtual. And I'd like to introduce the speaker today, with is Katarina Blask. She will be presenting for her colleagues, Marie-Louise Mueller, Mark Lotz, and Stephanie Crawford from Leibniz Institute for Psychology. The presentation today will be entitled D-Psy-FAIR, the Development of Documentation Standard Enabling a Sustainable, High-Quality Documentation of Psychological Research Data. Thank you.
Yeah, thank you for the kind introduction, and welcome everybody to my talk, which is aimed at introducing the D-Psy-FAIR standard, as already said. Yeah, before I start with introducing the standard, I would like to present the main goals and objectives of the Curation project, as well as the work schedule, which was realized in this project to finally come up with the D-Psy-FAIR standard. So let me start with a short description of the goals and objectives of the Curation project, which was funded by the Federal Ministry of Education and Research. So the primary goal was to develop user-oriented curation criteria for psychological research data. And these criteria should take into account the method-specific requirements of the data collection process in psychology. On the one hand, this strategic goal aims at improving and facilitating the reusability of research data. And on the other hand, we wanted to transform these criteria into a coherent and easy-to-use documentation standard to increase the willingness and also the ability of researchers to share their research data. Yeah, and to reach this goal, we first identified, of course, existing curation criteria and standards for psychological research data. And the primary result of this status quo analysis was that even though there's a large number of standards, they do not adequately match the documentation requirements of the psychological research process. So in order to specify these requirements, we conducted then some expert interviews and an online survey. And the main results of these two studies, so the expert interviews and the online survey, were that a standard for the documentation of psychological research data should contain metadata on the research design, hypothesis. It should contain administrative metadata, so information on the author's name, funding, and so on. It should contain a study protocol and also a comprehensive description of all variables included in the data. So in other words, it should contain a code book. And so here on the right side of the screen, you can see the first prototype of our documentation standard with which we came up. This prototype for the contextual specification of our standard consists of essentially 3 levels of description for your data. Levels 1 and 2 describe the study design at a construct level and also at the operational level. And level 3, which is presented here in the lower part of the graphic, is aimed at the documentation or comprehensive description of the entire research process underlying the data, including, for instance, information on the used study materials, scripts, program code, and so on. Okay, after we had detailed the contextual specification of our standard, we were, of course, interested in finding the optimal presentation mode for this information. So in defining a formal specification for our standard. And so we conducted 2 user studies aimed at finding the best suited presentation mode for all the information included in our standard. And yeah, the first study revealed that our formal specification of the standard is too technical to be of optimal use for psychological researchers when reusing data. And yeah, in particular, researchers told us that they needed more guidance regarding the standard and a more structured presentation of the information. And so we revised our formal specification and did the second user study. And after analysis of all the results from these 2 user studies and an integration in a formal concept, in an updated formal concept, we ended up with the formal specification displayed here on the right of the screen. So there's essentially a parent folder, which you can see here. And this folder includes the study description and an overview of all the files included in the parent folder. So a typical README file, I think most researchers already include such a README file in their documentation. Yeah, and within this parent folder, you have several child folders, including different information pieces. So here you have a data folder, a codebook folder, and so on. Yeah, and after we had developed our standard and had defined the contextual and formal specification, we were, of course, also interested in estimating its usability. Because in our project proposal, we wrote that we want to develop curation criteria that are usable for researchers in their role as data users and also data providers. So we had to check for this. And in particular, we wanted to know so whether it is perceived as user-friendly as it should be. Therefore, we conducted a 3rd user study, and we also finished a 4th one last week. Yeah, results of the 3rd user study, in which we compared participants' effectiveness and efficiency in reusing data documented in accordance with our standard compared to data documented with another comparable standard, revealed that participants actually perceived our data or data that were documented in accordance with our standard to be more usable. And participants were also more accurate in task completion when using data and documentation which were in accordance with our standard. So now we found this would be a good time to name our baby. And here on the right, you can see with what we came up. The standard is now called D-Psy-FAIR, including the promise that using this standard provides other researchers a key to your data, thus increasing their reusability. Yeah, and now let me briefly discuss the concrete implementation of the standard. The D-Psy-FAIR standard comprises 4 steps, which you can see here. And these 4 steps have to be implemented for the creation of sustainable data documentation. The first is the creation of a comprehensive study description, which ultimately corresponds to the writing of a method report or the labeling of your data with content metadata. Content metadata in this context can be, for example, those that reflect the hypothesis of the study or the research design. And in the second step, documentation is then carried out at the dataset level via the creation of a codebook, which provides a comprehensive description of all variables contained in the dataset. In addition to the dataset itself, there are, of course, in most cases, also data preparation and analysis scripts, which, of course, also require comprehensible documentation. Specifically, one should pay attention to an easy-to-comprehend description of all data preparation and analysis steps, which one has carried out during the data preparation and analysis process. Yeah, and last but not least, one should create an overview graphic that reflects all the important steps of the research process underlying the data. This is essentially meant to just integrate the different information pieces which researchers produce when documenting the data. Okay. In the case of the first two steps, we are in the fortunate position that we were already able to implement the corresponding software solution during the project term. So we have implemented both the input of the content metadata for the study description and the creation of the codebook in the improved new version of the data management assistance system DataWiz. So here you can see a screenshot of the input mask for the study description within this tool. Researchers can fill in here all the information that is needed to understand the study, which has been conducted in order to produce the data that are documented now. Here and here is the corresponding input mask for the codebook, the so-called codebook editor, where researchers can add all the relevant attributes to their variables. So like name, label, item text, and they can define the missings and value labels. Okay, for the third and fourth step, we are currently working on a corresponding software solution, but unfortunately, we do not have anything presentable yet. However, to give you an idea of how these documentation steps could be realized, I have brought two more slides showing an example of these documentation steps. So regarding the third step, I would presume that most psychologists already do this in one way or another. However, the most important aspect about step 3, so the documentation of your data preparation and analysis scripts, is that the code snippets corresponding to a certain data preparation or analysis task should be described in a way allowing other researchers to do exactly the same thing in their own analysis software. So you have to describe it in a rather generic way, which is independent of a certain script language or something like that. Okay, and here you can now see an example of how you can create a graphical overview of the entire research data process. Such an overview graphic essentially consists of 4 levels. You start with a description of the study details and the research design. These are levels 1 and 2. And then you move on to the measurement level, where you describe all the measurement instruments in relation to the specific measurement goal and the methods used to achieve this goal. And finally, you end your graphical overview by assigning the data, or more precisely the variables, to the measurement tools or goals from whose application they emerged. Yeah, and before we get into the discussion, let me perhaps briefly formulate the take-home message for the standard. So here it comes. The D-Psy-FAIR standard enables method-specific, user-friendly, high-quality and sustainable data documentation in just 4 steps. I think this is decisive that it is only 4 steps. Of course, writing a code book can also take a lot of time. If you have a lot of variables, but nevertheless, 4 steps, that's not so much. Okay, then it's time to thank you for your attention, and now I'm curious about the discussion. Thank you.
Thank you, Katarina. We do have time for a few questions, if there are any here in the audience or any from online.
Thank you so much. I have a question for the last speaker about the D-Psy-FAIR. One question is, I saw a lot of CSV and PDF files. Is it and FAIR is in your name? Is it also machine readable and machine actionable, or is that planned?
Mhm. Yeah, in DataWiz, you can also produce the machine readable files, so JSON files, for instance. But the goal of our project was not only to produce machine readable files or machine readable metadata and another metadata standard that is fair in terms of machine readable. But we concentrated on creating a standard that is in the foreground, human actionable, so to say, so that humans can use the standard to document the data. And the machine actionable thing is rather in the background, but it exists.
Okay, thanks so much. And the tool is also available for others to use if I.
We have a GitHub repository, and so you can also implement it on your local PC if you want to.
Thank you so much.
Okay.
Thank you. Are there any other questions here in the room? I don't know if we have any online. Did we have any? No. Okay. Well, thank you very much. Let's thank all of our presenters for their wonderful presentations. And I want to thank the audience, both online and in person, and our wonderful help that we've had with our technical support today. Thank you. I guess it's time for posters, if I'm not mistaken, and we'll all be heading out the door for that. Thank you so much.